Let's take a look at logarithmic functions. In the previous section, we talked about exponential functions. So let me recall what we did in the previous section. We called the function f of x or y equal a to the x without a coefficient in front of it, assuming the coefficient in front is 1. And we call that the exponential function. Now, the function we mentioned was 1 to 1, therefore it is possible to find its inverse. Now, in trying to finding the inverse here, that's what we want to know. We want to know what is the inverse of this function. So we're going to go through, remember, to find the inverse, we went through a two-step process also that was earlier. I believe it was 2 lectures back when we talked about one-to-one functions. To find the inverse function, we make a swap. We swap the x and the y. And if possible, we solve for y, and we call that the inverse function. So at this point, the moment you make the swap, this is the inverse function. That's what that is, the inverse. It's just, it is not in its explicit form. It's the implicit form of the inverse. The implicit form, that means we haven't solved for x. X and y are in an equation combined together. Now at this point, we can redefine this inverse function. We can redefine it as y equal log base a of x. Okay, so the logarithmic form is just simply another way to write the exponential equations. All right, and this goes back to the time of Napier, when he actually developed or discovered the whole idea of logarithms, John Napier. And so for us, it's just another rewrite of exponential forms. Notice in the exponential form, we have 3 components, a, x, and y. And in the logarithmic form, we have the same 3 components. It's just a repositioning of those 3 items, okay, which enables us to solve for y. Now, let's take a look at, in terms of the properties, and also, by the way, when we did exponential function, we mentioned a cannot be 1 and a has to be positive. Well, same holds for logarithmic function, because remember, logs are exponentials. It's just a rewrite of exponential functions. Okay. Now, in terms of the graph of logarithm, let's say I'm looking at the general graph of exponential functions whose base is larger than 1. Again, we looked at these before. The basic exponential function goes through point 0, 1. And because of the symmetry with respect to the line y equal x, we can actually graph the inverse function. So point 0, 1 is going to become 1, 0. And this is how the graph of the inverse is going to look like. So this portion of the graph is here, and this portion of the graph is here. All right. And we have the graph of the inverse. Now the inverse is the log, so this is the graph of log x in base a. All log functions go through point 1, 0, just as exponential functions went through point 0, 1. Except now they go through the x-intercept rather than y-intercept. With respect to the exponential function, we had the horizontal asymptote, which was the x-axis. Now we have the y-axis as the vertical asymptote. So let's write the properties that we see here for the logarithmic function. First of all, the domain of logs are the same as the range of the exponents, right? The functions which created them as inverses. So that means the domain is from 0 to infinity. That was the range of the exponential function. The range of logarithmic functions go from negative infinity to the infinity. And again, that was the domain of the exponential function. What else? The function is indeed 1 to 1. it has an inverse, and its inverse we already know is the exponential function. The function is increasing over the entire domain from 0 to infinity. Okay, what about the xy intercept? The x-intercept this time is going to be at 1, 0. There is no y-intercept. Y-intercept, none. And there's actually a vertical asymptote of the graph of the function. The vertical asymptote is going to be the y-axis. So it's going to be the line x equals 0. All right, so those are again the key highlights of the logarithmic function. Now, if the base of the log lies between 0 and 1, the graph is going to look like this. There you go. That will be the graph of the log function for bases that are between 0 and 1. Okay. And everything we said here still works, except instead of increasing, now it's going to be decreasing. The function is going to be decreasing. All right. Now, we do have certain bases of logarithms that occur frequently. So let's talk about these special logarithms. Special logarithms. These special logarithms are the ones that have the following bases. First, the base of the log is going to be 2. The base of the log could be e, and the base of the log could be 10. Those are the most common bases that we work with. Now, a log that has base 2. Now, a lot of math textbooks don't write this one, but computer science textbooks quite often have information with log base 2, and that's obvious, I guess, being computer logic working based on 0, 1. So base 2 would make sense for computer sciences to work on. So let's write this one. A log base 2 of x. The name of this is actually, they call it log of x. Okay, and it's just base 2. The graph of log base 2x is just like any valid logarithm whose base is greater than 1. So this would be the graph of log base 2. Let me see, it's actually more like this. There you go. This is log base 2 of x. Now, as far as the write-up of log base 2 of x, quite often we use the letter LG of x. LG means log of x. Okay, so that's what LG of x looks like. Here's LG of x. Okay, so we have that one. Then we look at the log base 10. The log base 10 of x, it's called the common log. And it's common because the old math textbooks, it was common to all math textbooks. They used to have the table of values of logarithms with base 10. This is like in the early 80s and prior, okay, where calculators were not so prevalent. So a long time ago, over, I don't know, 45 years ago, they used to be in the textbooks, mathematic textbooks. Now, if the base of the log is 10, we simply don't write it. Okay, and that's just one way to prevent from writing. Notice the 10 is missing now. So we call that the common log. Okay, the graph of a common log is almost like log of x, except it's going to turn much sharper in this direction. There you go. So that's common log of x. And this part of it, it drops more drastically also. Now, a log that has base e, this log base e of x, this is called a natural log. And again, the reference for the name, natural log, because a lot of the growth models in biological studies, and hence nature, word natural, follow this kind of a log. For the natural log base e of x, again, if we don't want to write the base e, we usually use ln. In fact, there you go, ln of x. That's how we read this natural log of x. That's what that is, ln of x. The natural log of x, or the ln of x, is also called the Naperian log. Naperian log. And it's named in honor of the Scottish mathematician John Napier, who actually developed the whole idea of logarithms and spent almost all of entire his adult life over developing properties and tables, massive tables of logarithms, so other people can use it. And I should also say that Napier's approach to logarithms were quite different than what we're doing right now, and it has nothing to do with the way we define logarithms. The word logarithm, by the way, going back since I mentioned Napier, is putting together logos, arithmus. If you put these two words together, you get logarithm. There you go. See, that is juxtaposition of these two words, which the literal meaning of these in Latin, logos arithmus. Arithmus means arithmetic. Arithmetic. Okay, and logos here means ratio. Now, arithmetic or numbers in this case. So, logarithm, again, put together logos arithmus, means ratio of numbers. That's what the literal meaning of logarithm is. Ratio of numbers. And again, it had to do with the approach Napier took in developing the idea of logarithms. And he's also famous for Napier bones. Okay, so you can actually do a Google on that, or go to Wikipedia and read about Napier bones. Very interesting. It's like kind of like an abacus that does addition and multiplication. All right. So having talked about these logarithms, what does the natural log look like? Where natural log is log base e, and remember e is approximately 2.718, right? Therefore, the graph of a natural log looks like almost like log base. There you go. It's almost log base 3, and there is the graph of that one. So those are some very special logarithms that we use throughout. Typically in calculus courses, we use natural log quite often because of simplicity of their use. Okay, so let's take a look at some examples here. In this example, let's say I have a squared equal 1.6. We want to rewrite this in logarithmic form. So here's log for log. Now remember, there are three things. The base in the exponent will remain the base in the logarithmic form. And then the number that appears as exponent on a, that actually goes by itself on the other side of equal sign. The 1.6 goes in front of g. There you go, 1.6. And that is simply the rewrite. Both of these expressions are equivalent. Okay. Now, as far as the anatomy of logarithm goes, by the way, let me go back to this in this form. X is referred to as the argument of the logarithm. Okay, that's what X is. A is the base of the logarithm. So every logarithm is made up of argument and the base. So that's the rewrite of that one. Another example, what if I have e to the x is equal to 8? Well, for this one, again, here's log. The base would be unchanged, e. X goes on the other side. The exponent on base goes on the other side of the equal sign. And 8 goes in front of letter g. And note in both cases, by the way, you look at a squared, e to the x in logarithmic form. So I usually do this just to check and make sure that e and x, and in this case a and 2, are going to be positioned correctly in their exponential form. Okay. All right, let's do another rewrite. And by the way, log base e of 8, we can write this as ln of 8 equal x, right? That's just a shorthand for log base e. Now let's change, for example, from log to exponential forms. In this example, suppose I have natural log of 4 equal x, and we want to rewrite it. Well, ln of 4, remember, that's just log base e of 4. And in the exponential form, we position e and x in the following manner. Here's base e remains base, x goes to the exponent, and 4 has to go on the other side by itself. So it's just a matter of repositioning those three things. Okay, let's do another example. Let's say in this next example, I'm going to have log 2 base 3 equal x. So how am I going to position those in exponential form? Well, that means 3 to the x is equal to 2. And there I have that one. And it's really all you got to do. Notice logs and exponentials are the same, so we just rewrite them in different forms. In this next example, let's say I want to find the exact values now. Find exact value of an expression. What is the expression? Let's say the expression is log 1 in base 2. I want to know what this equals to without the use of a calculator. So to evaluate this, I'm going to rewrite it using exponential forms, because that's the only way I understand logarithms, in their exponential form. And how is this going to look like? That means 2 to the power of question mark equals 1. And at this point, I just kind of do a guess and check, or trial and error. 2 to what power is 1? Well, 2 to the first power is 2, not 1. 0, correct? 2 to 0, because anything to 0 is 1. Therefore, the answer is 0. So log 1 in base 2 is 0. In fact, base could be 20. Base could be any valid base, right? Log 1 in any valid base, a, is 0. And we're going to actually make that one of many properties of logarithms. Okay, so we have that one. Now, let's do another one. Suppose I want to again find the exact value of, let's stay with log. Let's say I want to do log base 7 of 49. We want to know what this equals to. And again, by definition of logs, that means 7 to the power, to what power is 49? So the answer to the log is the power to which you raise the base to get 49. And in this case, again, by inspection, yes, 7 squared is 49, correct? So the answer is 2. That will be the exact value without the use of a calculator. Now let's take a look at this one. Let's say I have natural log of the square root of e. And I want to evaluate this one without a calculator. So I'm going to rewrite ln as log base e of square root of e, right? And we want to know what this equals to. We'll go in off of definition of logarithms again. That means e to what power is equal to square root of e. Now, square root of e, we can rewrite the square roots using rational exponents. So this is going to be e to 1/2, right? Therefore, the question mark must be 1/2. Aha, there you go. Without a calculator. There is the answer to that one. Now, next example, let's work with logarithms. And in this one, I want to find the domain. Okay, let's find the domain of the logarithm. And this one, f of x, I'm going to make it a little more general than the ones we have worked with. Say this is log base 4 of x over 2 minus 5, something like that. Now, going back to when we talked about logarithms, the base of a logarithm has to be positive. The argument of it, I'm sorry, not the base. The base has to be positive, but also we're talking about domain. The domain of logarithms are values where the argument of the log is positive. Okay? So, in other words, this is what we're saying. This is the argument of a log. That argument has to be positive, not even 0. So we're going to go x squared minus 5 greater than 0. Okay, and then we can solve x over 2 greater than 5 multiplied by 2, so x has to be greater than 10. That means the domain of this expression is anywhere from 10 to infinity. And you can try, for example, try 9, and you will see that, or try, I don't know, 8. If I try 8, I get 8 halves minus 5, which is 4 minus 5, negative 1. And log of negative 1 is undefined. Okay, because if you look at the graph of log, see, domain has to be positive. And negative 1, there is no graph here. So there's no value of the function beyond 0. All right, so that will be the domain for 10 to infinity or x greater than 10. Let's do another one. Let's say I want to find the domain of this one. Another example. Let's say I have ln of 1 over x plus 1. Again, doesn't matter where you have common log, log, or natural log. All domains for the argument of the logs have to be positive. So I'm going to do 1 over x plus 1 has to be positive. And this one we can use again the method of chapter 4. Let's see what makes, because I have 0 here and the factored form on the left side. This is a rational expression on the left side. So what makes the denominator 0 is negative 1. And because division by 0 at that point is undefined, I have an open circle. And then we pick a test point such as 0, 1 over 0 plus 1 is 1 over 1, which is 1, which is positive. So I'll pick up my sign chart this way. Consequently, below negative 1 is negative 1. I mean, it's negative. The sign on the fraction is negative. And we want the domain of the log to be positive. So here's where we get the positive segment of the number line. So the domain of this expression is from negative 1 to infinity. If you put negative 1, you get division by 0, 1 over 0, which is undefined. And anything beyond that should work. Okay. Let's try another domain. Let's say for this one, I have f of x equals square root and then natural log of x. Now for this one, we have to think about two things. One is for any square root, the radicand must be positive, right? The radicand has to be greater than or equal to 0. So in other words, we say ln of x has to be greater than or equal to 0. And then for this one, I'll do it a couple of ways. If I look at the graph of natural log of x, the graph looks like this for ln of x. For the function to be positive, greater than 0 means positive. So there you go. The function is positive for all the points, right, for x values to the right of 1, and it's 0 at 1. Therefore, the domain of this function is going to be from 1 to infinity. And remember, for domain, we look at the x-axis, right? That's going to be the domain. For range, you look at the y-axis. So we go from 1 to infinity. From 1 to infinity, the natural log is positive. Another way I could have done it is to write ln of x, which is log base e of x. We want this to be at least 0. Again, rewrite this in the exponential form. That means x has to be greater than or equal to e to 0, right? And e to 0 is 1, so x must be greater than or equal to 1. And there is a set builder notation for the same thing. All right. Now let's see. Let's do one where we have to find the domain and graph the function, get the range, and I'll do a whole gamut on this one. We're gonna run the whole 9 yard on this one. So we want to find the domain of f. We want to graph it, and we also, from the graph, we can get the range and any asymptotes, and let's do the inverse while we are at it also, and all that information about the inverse. So let's say my function y is equal to natural log of x plus 4. Okay, first of all, the domain. The domain of this is going to be x plus 4 has to be greater than 0. Remember, argument of a log has to be positive. So x must be greater than -4. That means -4 to infinity. So that is the domain. Now the domain of the function, this is going to be also the range of f inverse, isn't it? Right, the range of f inverse. And what is the range of the function? The range of logarithm ln is going to be -infinity to infinity, which means that's going to be the domain of the inverse. We talked about a function and its inverse earlier in, I believe it was section 2. Yeah, 2 lectures back. Okay, so we got those information. Let's graph the natural log. Now, if I think of, let's say, g of x as ln of x, then think about g of x minus h. That's going to be ln of x minus h, right? Because I have x plus 4 here. So I'm thinking this is the ln of x plus 4 is going to be like g at x plus 4, right? Which we can write it as x minus -4. So I have my h. H is -4, less than 0. So there's going to be a shift to the left of 4 units, right? Horizontal shift to the left of the graph of natural log of x. And here it is. This is the graph of natural log of x. Okay, it goes through 0.10. The graph of ln of x plus 4 is going to be shifted to the left 4 units. This is 1, 2, 3, 4. Now the vertical asymptote, which is the y-axis, also shifts, which is at 0, goes to the left 4 units. So it's now at -4. What used to be at x equals 0 is now at x equals -4. That's the vertical asymptote. Then I'm just going to redraw my log function. There you go. And that is the graph. Okay, so the x-intercept is going to be at -3, 0. You can try it when you put -3 here. -3 plus 4 makes 1, and natural log of 1 is 0. Okay, and maybe I do this ln of x dotted because that's not the primary graph. All right, so we have everything that we needed, and it makes sense for the function. Here is the domain of the function. X is greater than -4, and that's what we set up here. The ranges are real numbers, and we are good. We found the vertical asymptotes. This is the vertical asymptote. The y-intercept, that's when the function is, when x is 0, right? You go 0 plus 4, so that's going to be ln of 4. The y-intercept is at 0 and natural log of 4. and that would be here, whatever that number is. And I probably need a calculator for that one. But that's the y-intercept, 0 and ln of 4. Okay, and we found the x-intercept. The x-intercept is at -3 and 0. All right, and just about everything we wanted from this graph. Now, let's do the inverse. For the inverse, all right, for the inverse, we're going to switch the x and the y, right? Or actually do this. Remember, y is ln of x plus 4. So I can write it as log base e of x plus 4. That's what y is, correct? Rewrite in exponential form. So e to the y is x plus 4. And then at this point, what do? We switch x and y, right? Or swap. So we have e to the x equal y plus 4, and then solved, or two-step. To solve for y, we subtract 4 from both sides, and there is the inverse function. The inverse is going to be an exponential function. Now, the inverse function is going to be e to the x minus 4. This is the graph of e to the x, right? We saw that earlier in the previous section. E to the x minus 4 drops the floor, which is the horizontal asymptote, and the entire graph 1, 2, 3, 4 units down. The old horizontal asymptote, which is at y0, now appears at y equals -4, because we're transforming it down 4 units. Okay, and then redraw this graph. Here we have this one. And this is -3 now. What used to be at 1 is now at -3. And everything that we need, we can get from the graph. So domain, and remember, this is the inverse now. Domain of the inverse is all real numbers. The range of the inverse, and we found these earlier too, ranges from -3 to infinity. See up here? We did the domain of the function, domain of f, right in here, was from -4 to infinity. Oh, the range is going to be -4, because this is -4. There you go. The graph is above -4. Again, we found these earlier too. For this one, the x-intercept, what used to be the y-intercept is now the x-intercept. But the y-intercept is easy to do. That's e to 0 minus 4. E to 0 is 1. 1 minus 4, -3. So that's 0, -3, right in here. Okay, and this one has a horizontal asymptote, no vertical asymptote. Horizontal asymptote is y equal -4. Okay. And there we have this one. Let's see, if I want to find the x-intercept, I may have to use a calculator for this one. The x-intercept, that's when e to the x, actually no I don't. We set the function equal to 0, right? The inverse function. Now, solve for x. E to the x, add 4 to both sides. Now this one we can solve. We are in a position to solve this. Let's rewrite this in logarithmic form. Base is e, 4 goes in front, and x goes on the other side. And there we have it. Therefore, x is log base e of 4, which is natural log of 4. So my x-intercept therefore has the coordinates natural log of 4 comma 0. And look at 0 ln of 4 for the log function, and this is for the inverse function, the exponential function. Okay, and we are good with this one. Okay, now let's Let's finish this off with just maybe another example, one last example. This time we want to solve equations. Okay, let's say we want to solve e to the 3x equals 10. Now, to solve this, I'm going to rewrite it in logarithmic form. Okay, so that's log base e of 10 equals 3x. You see that? And how are we going to do this one? Well, all I have to do is solve for x, right? Remember, log base e of 10 is natural log of 10. So that means 3x equals natural log of 10. Divide both sides by 3. The answer is ln of 10 over 3. The exact value without a calculator. Okay, so that's what that is. And since that one went quick, let's do one last one. Suppose I have log base 2 of 3x plus 4. Okay, we do more logarithmic equations in another section, but for these are fairly easy to do. So I want to solve for x. Now let's rewrite it as 3x plus 4 equals 2 to the 5th. Rewrite using exponential form. And 2 to the 5th, that's 32. Now 3x is 32 minus 4, which is 28. Divide by 3, we get 28 thirds. Okay, and 28 thirds is a positive number. When I try it in my domain, I'm going to end up with a positive number, so I'm good. I'm in the domain of the function. What is the domain of this function, by the way? The domain argument must be positive. So as long as the answer is x greater than negative 4 thirds, we are okay. And definitely 28 thirds is greater than that. So we are good. And there you have it. With that, we are done with this section, logarithmic functions, and we did some simple logarithmic equations as well. In our next section, we're gonna, or lecture, I should say, we're gonna look at some properties of logarithms in that next section. So as always, thank you for watching again, and hope to have you in another lecture.